Let's give it up for Liu.
Hello, everyone. Welcome to An Idiot's Guide to Building a Language in TypeScript. I'd just like to make it absolutely clear. There's an asterisk there because An Idiot's Guide is a little bit ambiguous. It's not a guide for idiots. It's an idiot guiding you. Yeah, this is going to go great. So the first question I get asked is, hi, who are you? And the second one is where in my house, but my name is... this is going down the drain already. I work as an innovation and outreach lead at Voxer, so basically I smile, shake hands, and do corporate stuff. I write code and give talks, albeit not very good ones. I'm chaotic neutral because I use TypeScript, and also I'm an evil genius with a killer fashion sense. And speaking of, let me just I'm gonna just give me a minute. Absolutely fabulous. And that is my corporate photograph. That is what other people know me as compared to this. So, you want to build your own language. Maybe you want to feel smart, maybe you want to feel a little bit vain and have something named after you. Maybe you're bored, maybe you're incredibly sad. We won't have time to run through the entire implementation, so we'll only touch on the different bits of an interpreted language, a few interesting architectural decisions, and also building a REPL with the REPL package. But effectively, this is a talk about getting to grips with language design, making terrible decisions, and also making something fun that you can talk about. So the first question is, why build a programming language? And for me personally, it's because I like experimenting with things. I've always been fascinated with the fact that we can take something that we understand and we can make computers, which can only process ones and zeros and bits and bytes. They can do stuff with that. I like a challenge, even though building a language isn't as hard as I thought it would be. It's an excellent project for implementing TDD because you can treat all your different bits and pieces as black boxes and test against them, test their behaviors. And also you learn a lot about language design and you learn a lot about how to use your base programming language. But above all, the reason that I built an interpreted programming language is because I'm incredibly sad. I can hear some of you, smart cookies in the audience, talking about context-free grammar and why not just, this comic is my favorite. Why build a programming language and that's already a solved problem? And it's because you want to build, and thank you very much, you get the comic, sir. It's because I want to build from scratch. And it's interesting understanding how these problems are solved and how exactly programming languages work under the hood. So before we do any of that, before we actually build a programming language, before we create this abomination, we have to actually, we have to define what exactly a programming language is. And for our intents and purposes, a programming language is basically a set of rules that we can use to give a computer instructions. It's very, very structured, and it gives us a structured space within which to work. It's defined on 3 levels: the lexical, or what words are, the syntactical, or what grammar is, and the semantic, or what meaning is. And breaking it down like this begs the question, how exactly do we define each level? How do we define the syntactical, the lexical, the syntactic, and the semantic? So, drawing some parallels in English, the words in all programming languages are lexemes. So a lexeme is a string of 1 or more characters, and that can convey some degree of meaning. We have if and else, we have while, we have plus, minus, asterisk, we have X, Y, or Z. And similar to English, we actually have words that can convey degrees of meaning. For example, about, green, the, supercalifragilisticexpialidocious, and my personal favorite, anti-disestablishmentarianism. So these are all words, thank you very much. These are all words that we can use to convey meaning. Now, the smarter among you may have realized that if we can have lexemes such as X, Y, and Z, that means we can have, effectively, an infinite number of lexemes, because identifiers are lexemes. So anything that you can think of conveys meaning or can convey meaning within your programming language. And so to get around this problem and to actually make the bits of all programming language useful, what we do is we classify them. We classify all words into tokens. Just like we can classify words into nouns and adverbs and adjectives and verbs, what we can do is we can classify each lexeme as a token. So we can classify it as an identifier, an operator, be it prefix, mixfix, or infix. We can identify, shoot, my mind's gone blank. we can classify our lexemes as, but you'll see in a minute. And this entire process is called lexical analysis, which is performed by the lexer, quite obviously. So the first bit, coming in from the left, is the fact that we have a lexer which breaks our input into a series of tokens, and then from that, we can extract some graphemes. Or from that, we extract graphemes to build the lexer. Let's actually take a look at that. So I'm just gonna do that. I also don't have a PhD, meaning I'm gonna struggle with this a bit. Solid. Right. What we can do is I'm just going to swipe up, and we can take a look at our terminal here. And what we can do is we can run this in Lex mode, and we can put some input in. Let me just make that a little bit bigger. There we go. We can actually Lex our input. So I can say let x equals 7. Nope, that's bad. That's terrible. There's a bit of space there. And we can see that our token type, or our input's been broken down into the let token, an identifier, an equals, an integer, and a semicolon. And this first bit is actually the smartest piece of our lexer, or the smartest piece of our programming language, because what it does is it can take this soup of words and put it into some defined structure that the computer can understand. And from that, we can perform other steps. I can also say something like x equals 5, or x minus 5. And as you can see here, the lexer is only responsible for breaking down the different bits and pieces of our programming language. It doesn't actually define whether they're valid, because x minus 5, x can be defined, x cannot be defined, x could even be a string for all we know. I can also do something like, hello, God, I hate typing. Hello world. God damn it. And we can see that it identifies that as a string. So that, overall, is just our lexer. If I now just swipe up, that's not working. There we go. So that gives us an overview of our lexer. There are actually a couple of very, very interesting things when it comes to building a lexer. This is actually the code behind it. One of the most interesting things here is we actually use regular expressions with Unicode properties, which is something that I didn't know about. Unicode can now say, this is a letter, this is an emoji, this is a number, and this is white space. And we can use those regular expressions to consume white space or to identify particular characters, figure out whether something's a valid number or not, and so on and so forth. After that, we have to define the syntactical. So what exactly is grammar? And getting the computer to understand what is syntactically valid in our language does seem a bit difficult, but we can create an algorithm called a parser for processing our tokens and generating a set of nodes. So we can define an expression like hello, multiply world is invalid, or 4 times 16 or negative 22 is valid based on token type, based on order, and based on a bunch of other information. I use Pratt parsing, basically identifies the precedence of each operator and defines a set of, and groups them accordingly. So for example, we can have something like 1 times 2 plus 3, which is ambiguous, and it groups them 1 and 2 because multiply has a higher precedence than addition. And 1 plus 2 times 3, 2 times 3 is grouped together because we have a higher precedence. This, on a more technical level, is how it works. We have an infix operator, and it can say, hey, we've got an integer literal, so it starts on the left here, got an integer, and on the right, oops, that wasn't supposed to happen. And on the right, we have a multiplier, and then what the parser can do is it can say, hey, these 2 expressions here will need to be multiplied before we have the 1, which gives us an order of operations, which is something that's incredibly powerful. We can say, hey, we want to do this operation first, and then this, without without too much logic involved. And we can also introduce the concept of environments, where we have an integer in or assigned to x, and then we can pull that into our, or parser can define that, or parser can create a, can basically define that, and then we can pull that into our tree evaluation time. So we have expressions and statements. Expressions produce values, statements don't. And these are all defined by classes, which is very, very important when it comes to our next step. Coming in from the bottom, subverting expectations. Basically, we have a meaningless list of tokens, and we can give them some order or give them some semblance. And if we take a look at this, we can exit this, and we can clear, and we can start in AST mode, and we can say 1 plus 2 times 3, and shit, that's too big. We can, give me a second. We can see that we have an expression statement, which has our 1 on the left, and on the right, we have our 2 and our 3, which need to be multiplied first. And this is insane. We've gone from an unstructured list of numbers to a structured tree with an order of operations. It's black magic. It's just magic. Nobody knows how any of this works. After that, what we can do is we can give all words some meaning. So in this particular case, you can build a tree walking evaluator, or you can build any evaluator you want. And this is the best bit. Any piece of your programming language, you can swap out and replace with something else at any time, because you build the language and all the discrete parts, the lexer, the parser, and also the evaluator, they can be swapped out for one another. You can build whatever you want. You're going to love this. Coming in from the top. Basically, our evaluator evaluates. It says, hey, we have a semantic definition, and we can calculate the value of the statement by walking through each set of nodes. I am going to just click through that. Hold the applause, because this might actually not work. So if we pop into the... I'm going to start in evaluate mode. Right, this is nerve-wracking. 1 plus 2 times 3. God damn it. 1 plus 2 times 3. So 2 times 3 is 6, and 1 is 7. Hey, look at that. It actually produces 7. This is crazy. And we can do 1 times 2 plus 3. 1 second, plus 3. And that's 5. And we can say, let x equal 7. And that returns null. We can say x is 7. God damn it. And we can do x times 2, which won't be found. God damn it. So very close. So very close. But effectively, what we can do is we can have an environment, and we can put variables in that environment. We can evaluate those variables. And we've produced our very own programming language. Building a REPL is rather simple. It's basically, you take some input, you produce a result, you update the execution environment, and then you can repeat that. So if we take a look at the actual code here for the REPL, we've got the evaluation code here, and the part that we need to focus on is the evaluate mode here, which is basically, you evaluate, god damn it, there you go. You can evaluate a result and then return that and update your environment. Evaluate your result, return that, and update your environment. And this very, very basic structure is what most programming languages do. So building a programming language isn't that hard. If I can do it and it doesn't work, you can do it, and it most definitely will. God fucking damn it. Thank you very much.